All right, here are some practice questions for enthalpy change, calculating enthalpy change using bond energies. Or over here, the chemical equation shows the equation for the reaction that can be represented as shown. I think I misread the question, but you know what I mean. This is C2H4, and what they've done for us is they're showing all the bonds. And if a molecule's bonds aren't shown, you'll have to figure them out. But those sort of molecules will be a little simpler, right? Not crazy molecules like this. Anyway, C2H4 is reacting with chlorine, which is Cl2, forming this monstrosity. And they're saying the energy change for this reaction is negative 180 kilojoules per mole. So what does that mean? That means that the enthalpy change, delta H, is negative 180 kilojoules per mole. I feel a little lazy writing this down, but it's important, right? All right, calculate the energy needed to break the bonds. So what bonds are being broken? Well, this is a reaction. This is what was, these two things, and this is what it's turning into. So all of these bonds before the arrow, that's the arrow, before the arrow are being broken, and these are all being formed. So what do we need to do? We want to figure out all of these bonds energies and add them up. And where do we find these energies? Well, all of these energies are given to us. So we count the bonds and just figure it out. All right, let's do that. All right, now the image is outside of our view, but what bonds did we have? So over here, I counted 1 carbon-carbon double bond. I'm counting 4 carbon hydrogen bonds. I think we're done with the weird molecule. And there's only 1 chlorine-chlorine bond. So what I'm doing for myself is writing all the bonds down. Does that make sense? So what I'll do is, after this, now I've accounted for all the bonds, I'll replace it with the values. All right, let's do that now. Okay, so carbon double bond is 610. I see that in the table. It's right here. 610 plus 4 times, because there are 4 of them, 410 and 1, this bond. ClCl, which is 240. The energy needed, the sum of all of this is 2490 kilojoules, and that's the total energy, the sum of it, right? So what they've done is they've kind of made the question easier by dividing it into parts. They first asked only bond breaking, and in the second step they'll ask for bond forming, and they'll ask us to figure out what the total is, I'm guessing. Let's move on. All right, over here, the saying, use your answer in step 1 and the energy change of the reaction to determine the energy released when the bonds are formed. So what they've done is they already have given us delta H. We know that. I think it was negative 180 or something like that. I'll double check. But let's write down the equation. What's the equation? It's delta H equals to all the bond breaking energy minus all the energy from bond formation. This is negative 180. Bond breaking, we just calculated it. It was 2490 minus bond forming. So let's call it X. And we have to find this out. I think most of us will get the right answer, but note that your value is coming out to be positive. It's going to be 2670, right? All right, the next step is use your answer in step 2 and bond energy values to determine the energy of the CCl bond. So let's give ourselves some room like that, right? And so I've put the molecule over here so we can just analyze it. We know the energy released from when the bonds are formed, right? So what bonds are being formed? Well, it's the molecule on the right hand side, again, that has been redrawn over here, And all of these bonds are formed. So let's figure it out. Bond formed, bonds formed. I should have given myself more room. There is one carbon-carbon single bond, one carbon-chlorine bond, actually two of them, right? They're on each side, plus 4 carbon-hydrogen bonds. And it's just math from here. All right, bonds formed, this energy we already calculated. It's 2670. All of this is equal to, the carbon-carbon single bond energy is 350. Well, look at that, the fanciest 5 I've ever written down. I don't know the CCl bond, that's something we have to find out. I'll call one of them X. And there are 4 CHs, like last time. 410 again. So it's just a matter of math now, some algebra. Let's get the answer. This is pretty cool. I'm getting the answer as 340. Again, it's a positive energy, nothing negative over here. And that's interesting. So we did something reverse this time with this question. We figured out bond formed because the enthalpy change of the reaction was given. And with that, we found out the value for a missing bond, which is interesting, right? All right, let's move on to the next question. All right, nitrogen reacts with fluorine. So nitrogen reacting with fluorine, all the bonds are shown, kind of easy. All the energy of the bonds are shown. So let's skip to the question. We don't have to bother reading it. Highly unadvised, but I think we know what we're talking about. All right, calculate the energy taken in to break bonds. So what's being broken? Everything on the left-hand side of the equation. So what's that? Let me just adjust. So bonds being broken for short. All of this is equal to the energy or the total number of bonds broken. So seems like only a nitrogen triple bond is being broken. That's only one. Why did I even bother with the bracket? Who knows? But there are 3 fluorine-fluorine single bonds, correct? What is the energy for each of these? The nitrogen-nitrogen triple bond is 945 plus 3 times the fluorine-fluorine bond is 160. My answer comes out to 1425 kilojoules. So they've given kilojoules. If they don't give you kilojoules, you'll have to write the correct unit. Let's figure out the energy released when bonds are formed. So it is everything on the right hand side of the arrow. Formed. What is being formed? So it's only one molecule that's formed, right? And that molecule has a nitrogen fluorine type of bond only. One molecule has 3 of these bonds, so I'll have to count this energy thrice, but there are 2 molecules, so the entire thing will multiply by 2. So I could have just multiplied by 6. That's the same thing, right? If you don't understand this part, what I'm doing essentially is I have in the molecule 3 nitrogen fluorine bonds. So 1, 2, 3. I counted 3, but you're making 2 of these molecules. So how many bonds do you have? A total of 6, right? So 3 times 2 is 6. That's essentially what I'm doing. So let's solve it. So this energy is 300. So I think I'll just get 1800 as my answer. Moving down. Now I have to figure out what the change in energy is, right? Enthalpy change of the reaction is bonds broken. This is important to know. This is the correct order. Bonds formed, and we just calculated each of these. Bonds formed is 1425, and this is 1800. Now my answer is coming out to be negative, so I will make sure I'm putting in negative over here. Negative 375. Now when they're talking, so so far they haven't told us about enthalpy change. This is the first time in a long time, like since we started this thing, that they've asked for enthalpy change. Now enthalpy change for mine is coming out to be negative, so I'm putting a negative sign, implying that it's exothermic. If this value by any chance came out to be a positive value, the correct way, let's say it came out to be a positive 100, right? How would you write that? You cannot write just the number 100. That's not correct. यहाँ पे हम कर सकते हैं because it's the bond energy, but we're not doing that here, right? So enthalpy change has to have either a positive value or a negative value. Negative, a lot of times people just keep it there because, I mean, you're used to it from math. They don't write the positive if the energy comes out to be positive. You have to write the positive sign if it's a positive value. So enthalpy change, you'll say positive 100 or whatever the answer is. It's not, so I'll just ignore it, just an example. All right, so again, this negative sign right now is telling me what? That this is an exothermic reaction. Energy has been released. The next question is talking about the same thing, I believe. Use your answer to 1 to deduce whether this reaction is endothermic or exothermic. Explain your answer. It is exothermic. Why? Well, the value is negative, or you can say more energy was given out than absorbed, which means the same thing, because enthalpy change came out to be a negative value. Easy. This is not an energetics question. It's a dot and cross diagram, but I felt people were weak in dot and cross diagrams, so I just didn't feel like deleting this question. So fluorine has 7 bonds in its outer shell, nitrogen has 5. So let me draw all of the fluorines. 1, 2, 3, 4, 5, 6, and of course I'm sharing 1. And a little bit of, I can't explain why I'm sharing 1, but with a little bit of experience, you understand that group 7 elements, which is fluorine because it has 7 electrons, will share only one of its electrons to get 8, right? I think that makes sense. If you don't get it, you'll have to revise a lot more than looking at me solving past papers. So let me do the same thing for the other 3 fluorines real quick. So I just copied the same number of electrons and shared 1 for each fluorine. And nitrogen will share 1 over here, 1 over here, 1 over here. Oops. 1 over here. Nitrogen is now left with 2 electrons, and because it had 5, 3 it's shared, so I'll put them over here. And by doing that, I think nitrogen has 8 electrons in its shell, and each fluorine has 8. So this is a correct dot and cross diagram. Again, an equation is given to us, and I have to figure out energy needed to break the bonds. So let's do that real quick and spend less time reading the question, even though I don't recommend it. So broken, what's broken? Well, everything before this arrow is broken, right? Because that's what's reacting. So what do I have? Okay, there's a 4 over here. That's a lot. So I have the NH, right? How many NH bonds do I have? That's 1, 2, and 3. Right? So 3 for molecule and per molecule, and there are 4 of these molecules. So 3 times 4 is 12, right? I mean, yeah. What other bonds are broken is 5 of these oxygen double bonds. Now a double bond is different from a single bond. You notice over here there's no single bond oxygen given. Anyway, 4 oxygen double bonds. Okay. Okay, time to put in the values. It's 12 times this NH, which is 391, plus 4 times oxygen, 498. I'm getting a big number. It is 6684. I don't have to write positive, but when in doubt, just write positive because it is positive. It's not a negative value. All right, energy released from formation. Formed, why am I using this disgusting white? All right, what bonds are formed, looks like there are 4 nitrogen oxygen double bonds and 12 oxygen hydrogen bonds. What are their values? If we look at the question above, it is, what is it? Nitrogen oxygen is 4 times 5, 8, 7 plus 12 times OH, which is 4, 6, what is it? 4, 6, 4. Calculator time. 7916. Again, you can put a positive over here if you feel like it. Energy change when 1 mole of ammonia reacts. That's interesting. They're asking for 1 mole of ammonia. Well, in the equation, they've shown us 4 moles of ammonia. So for 4 moles, what is it going to be? Just the difference of these two values. Delta H is equal to bonds broken minus formed. So it's 6684 minus 7916, right? What is this coming out to be? I'm getting negative 1, 2, what is it? 3, 2. But that's for 4 moles. What would it be for 1 mole? So shouldn't it just be 1/4 of this value? If this is for 4 moles of ammonia reacting, then just divide it by 4, I'll get 308. And this time the value is negative. So 308. And that's my answer. Essentially, I divided this by 4. Right? Easy.